Hey everyone, and welcome to our second installment of lecture number 4 on congruences. And we had just sort of come up with a major result when we were talking about congruences last time. And here's the point. Every integer, k, is congruent to exactly one remainder modulo n. And that remainder is the remainder that we get when we divide k by n using the division algorithm. So maybe I shouldn't say it exactly like this. Maybe what I should say is there exists a unique R with R between 0 and n minus 1 such that k is congruent to R mod n if and only if k equals qn plus r, applying the division algorithm. And actually, this division algorithm itself guarantees that R is unique. So let's look at a couple of examples. Let's say that k equals 26 and n equals 8. By the division algorithm, we get k equals 3 times 8 plus 2. So here's our q, here's our k. And here's our remainder, R. Now what that means automatically is that 26 is congruent to the remainder 2 mod 8. That's what this is telling us. If we apply the division algorithm dividing by n, then k is congruent to its remainder when we divide by n. Let's look at some more examples. K equals 95, n equals 11. So let's apply the division algorithm. And 11 goes into 95 8 times, with a remainder of 7. So here's our quotient Q, here's the divisor N, here's our remainder. So what this tells us is that 95 is congruent to 7 modulo 8. And here's our remainder. And there's the divisor N. Now, an immediate consequence of the result that we just derived is the fact that two integers are congruent to each other modulo n exactly when they have the same remainder modulo n. And maybe I should put this characterization of congruence modulo n side by side with the one that we've been using before, namely that the difference of two integers, or rather, two integers are congruent exactly when their difference is a whole number multiple of n. So let's put those two characterizations of congruent modulo n side by side. They are equivalent, and we can use whichever characterization we want depending on the circumstances. You know what? Before I go on from this, let me correct something here. In my statement, I'm using n for two different things. So let me rewrite this correctly. I'll make my corrections in red. Let's say two integers k and m are congruent modulo n exactly when k and m are congruent to the same remainder modulo n. This is a correction of what I had written before. What I had written before was incorrect because I was using n to represent two different things. So if you're taking notes, please make this correction in your notes. And please don't sue me for malpractice either, even though I may deserve it for that gaffe. Okay, these are pretty much equivalent, well, these are equivalent statements. Integers k and m are congruent modulo n. That's the same as saying that the difference of k and m is a whole number multiple of n. That's also the same thing as saying that when we divide k by n and when we divide m by n using the division algorithm, we get the same remainder. And that's also the same as saying that k and m are congruent to the same remainder modulo n. So when we divide k and m by n, we get the same remainder modulo n, or k is congruent to that remainder, m is congruent to that remainder. Now, these are the biggies right here. These are the two criteria that we most commonly use to determine whether two integers k and m are congruent modulo n. Is their difference a whole number multiple of n? then they're congruent modulo n. Do k and m both have the same remainder when we divide by n? If they do, then they're congruent modulo n. And if they don't, then they're incongruent modulo n. Let's put this to use with some examples. I won't say put it to use, but let's illustrate it with some examples. And then we'll list some fundamental properties of congruences. Okay, our first example. Determine whether k equal 97 and m equal 34 are congruent modulo 9. So 9 is our n here. And we're going to do this two different ways. First, let's look at the difference and see if the difference is a whole number multiple of n. So we'll take k minus m. Oh. 7 minus 4 is 3. 9 minus 3 is 63. And yeah, that's a whole number multiple of 9, isn't it? So k is congruent to m modulo 9, where 9 is our n. And using the actual numbers, 97 is congruent to 34 modulo 9. Now, I did say that we were going to do this a different method. So let's do method number 2. K, let's see, if we divide k by n, if we divide 97 by n, that's going to be 10 times 9 plus 7. So there's our q, here's n, and here's our remainder. Okay. And what about m? M is 34. And if we divide that by n, that is, if we divide it by 9, we get 3 times 9, which is 27, remainder 7. So here's our q, here's our n, here's our remainder. K and m both have the same remainder when divided by 9. So k equals 97, and m equals, what is m? 34. Have the same remainder. When divided by n equal 9. Hence, 97 is congruent to 34 mod 9. Now let's do another example. Another example. Determine whether k equal 196 and m equal negative 36 are congruent modulo n equal 3. So the first method, we compute their difference and see if their difference is a whole number multiple of n equal 3. And what is that? 232? And 232 is not divisible by 3. Let's call it q. 232 is not equal to q times 3 for any integer q. So their difference is not a whole number multiple of 3. So k and m are incongruent mod 3, where 3 is our n. And speaking in terms of the numbers themselves, 196 and negative 36 are incongruent mod 3. So that's the way we can determine congruence or incongruence using the first criterion. Now let's use the second criterion. And that second criterion is, do they both yield the same remainder when we divide by n? Let's see. K is equal to 196, which equals something times 3 plus a remainder. Let's see. 3 goes into 19 6 times. 3 goes into 16 5 times with a remainder of 1. Let's see, did I do that right? 180 plus 15. Yep, I think I did. So here's my q, here's n, and here's my remainder. Now let's try m. M equals what? Negative 36, which is equal to something times negative 36 plus a remainder. Now I got to be careful here. Let's see. Holy moly. I did that wrong. Here's Q, here's N, and here's R. See, N is 3. N is our divisor. Now, let's see. Q is 36 is a multiple of 3, isn't it? So Q will be negative 12. And that will give us a remainder of 0. Okay. So K equal 196 and m equal negative 36 do not have the same remainder. When divided by n equal 3. So that means k is not congruent to m mod 3, where 3 is our n, or in terms of the numbers themselves, 196 is not congruent to negative 36 mod 3. So we get the same result, but it's just a different way of doing it. Method 1, we can see if the difference of two numbers is a whole number multiple of n. If their difference is a whole number multiple of n, then they're congruent modulo n, otherwise they're not. Or we can divide each number by n, and if they have the same remainder, they're congruent modulo n, otherwise they're not. And sometimes one criterion may be preferable to another, so it's good for us to know both. Okay, let's look at some properties of modulo arithmetic. First of all, every integer a is congruent to itself, modulo n, where n is just a natural number greater than or equal to 2. So I guess we'd call this what? Reflexive. Secondly, if a is congruent to b modulo n, then b is congruent to a modulo n, and vice versa. And I guess we'd call this symmetric. And if you didn't learn these terms in advanced math, don't worry about it. This is just for those who are familiar with the concepts. And let's see, next, if a is congruent to b mod n, and b is congruent to c mod n, then a is congruent to c mod n. So in Intro to Advanced Math lingo, I guess we'd say that congruence is a transitive relation as well. Now, in 4, we're supposing that a is congruent to b mod n, and c is congruent to d mod n. And so what we're doing here is we're taking the congruence a congruent to b, and we're adding congruent things, c and d, to each side of the congruence. So we're taking this congruence and we're adding c and d to both sides, where c and d are congruent themselves. And if a is congruent to b, then we can multiply both sides of a congruence by c and d, provided that c and d are also congruent. So we can multiply both sides of a congruence by congruent things, c and d. 5 is just a special case of 4 where c and d are equal. If a is congruent to b, then we can add the same number to both sides. If a is congruent to b, we can multiply both sides by the same number. And watch out, remember in our first part of lecture number 4, we can multiply both sides of a congruence by the same integer. But that doesn't mean we can divide both sides of a congruence by the same integer. There are specific circumstances where we can and specific circumstances where we can't divide both sides of a congruence by the same number. So if we start out with AC congruent to BC, that doesn't mean that we can cancel both sides, divide the C on both sides and come up with A congruent to B. That doesn't always work. And let's see, the last thing, and this is the one that I find absolutely mind-blowing. If I didn't know the math behind it, I would just bet my life that this wasn't true. But if A and B are congruent mod n, then we can raise A and B to the same natural number power, and we're going to get congruence mod n. If K is any natural number, we can raise both sides of a congruence to the power of K, and we still have congruent things. I would bet my life that that wasn't true if I didn't know what was behind this. It just seems too spectacular that these two things would turn out to be congruent. But in fact, they do. And in the next installment of lecture number 4, we're going to do several examples illustrating these properties.